アクセシビリティの話をしなかったので、今日
ちょっと
どうでしたか？なんでアクセシビリティがよくわからなかったので、でも飛ばしてしまって。
昨日復習会をやってた。
すみませんでした。Okay, so should we start? Are you all here? You are all here. I don't know. The others are. We don't know. Okay. I want to start on time. Okay. Thanks to you all for coming back. So I thought a little bit about the schedule that's on the web, and I think we can afford to cover some more of the things that were on the schedule yesterday in the first hour of today, and then move on to the Kratzer paper on ordering sources and so on. So I would like to say a little bit more about modal logic, because it's difficult, and especially if you've seen it for the first time yesterday, or if you haven't had very much experience with it, can be hard. And so just to repeat what we did yesterday, we talked about sets, right, which are just collections of, say, of objects, okay, and then relations, which just are sets of pairs, right? Except, well, at least if we're talking about binary relations, sets of pairs, and in general, of course, we can also have triples and quadruples and so on. But for our purposes, we only need to talk about pairs, right? And functions are relations that have these special properties. Remember, I said that from each element of the domain, you can go to just one element of the range, not more, right? Another way of saying that is that this relation is 2-1. You may be familiar with expressions like 1-to-1, right? Many-to-one, or one-to-many. Have you ever seen these things? Right, you say this in general about mappings from one thing to another. Well, this just says that relations that have this property are not functions, but the others are. Can be, well, this is one condition, as I said. Often it is also required that the domain of the function is covered entirely, that for every element of the domain you have something on the other side of the range. Right, so then yesterday we also talked about propositional logic, and there, so propositional logic, the language of propositional logic, syntax and semantics, interpretation relative to evaluation functions, right? And then some modal logic, propositional modal logic, right? Modal logic. So here we can say a little bit more today in this first hour at least. And I mean, I realize perhaps it was a little bit confusing that well, you said so, in fact, I know it was confusing that I used this symbol R interchangeably for an accessibility relation and a function from worlds to sets of worlds and so on. I still think it's fairly safe to do that. I mean, I did it on purpose actually. I thought it would be helpful. But so there are, to remind you, these two perspectives. So you have a model, right? Model M, say, for propositional modal logic would be a set of worlds, non-empty set W, right? And then we have this R and the valuation function. Remember, this was all on the board yesterday, right? Where V now is a function from worlds to truth assignments, giving truth values to sentences at each point individually, right? And now this R here, this is what I refer to in two ways. It's either a relation between worlds, so a relation, and in particular it's relation. It's called an accessibility relation. Accessibility relation, traditionally. Accessibility, yeah. And you know, the intuition is being that some worlds are accessible from your world of evaluation and others are not. This is how you see it in modal logic, and then you have expressions like this, W R W prime, which means that from world W, and you know, here suppose here's W prime, there is an arrow going from one to the other. Right, that's the statement. Whereas if you're thinking in terms of modal basis, which is the way Kratzer and others in the linguistic literature often talk about it, you have this function, right? So let's just call it a modal base, right? MB, a function from worlds to sets of worlds, and then this very same statement would become the claim that W prime is an element of RW. Because RW is the set of all the worlds, just those worlds that are accessible from W. Okay? There's really a very straightforward connection between these two perspectives. Likewise, if you have something, you claim like there is some W prime such that W R W prime, right? This kind of claim on the other side simply becomes, well, there is some W prime such that this is true, right? W prime is an element of RW. Which is, remember, the seriality of the relation corresponded to the non-emptiness of the modal base. Because this is the case if and only if RW is not empty. Right, if it's consistent. So we have this straightforward connection between these two perspectives. And we can stay with this a little bit longer perhaps. Well, first, so we have the model and now the interpretation of modalized sentences with these necessity and possibility operators. Right? Can also be defined in these two ways. So we want to assign a truth value at some world W to a sentence of the form, whatever, you know, box phi. And I write this R here, the intended accessibility relation, as a subscript, although if the model is fixed, then we could just we could put M up here, and then the R would also be implied by this, right? Which relation we are talking about, because the relation is part of the model. But since I did it on the handout, I wrote R here. Let's just go with this. And that is one if and only if for all W prime such that W R W prime, so for all accessible worlds, phi is true there, right? that simple. So we sort of peel off the operators, and if there are more, then they go away one by one, and so on. They are just like quantifiers. Likewise, on this side, we can say that the same sentence is one if and only if the set of worlds accessible from W is a subset of the set of worlds at which phi is true. In M. Okay. These are the same statement, equivalent statements. And possibility was just defined on this side here in the same way, but the only difference being that you have existential quantification here, right? For some W prime, and I'll skip the rest because it's the same. For some accessible world W prime, phi is true there, right? Yeah, I'm sorry, it's a bit hard to write like this. If you can't read my handwriting, please let me know. The idea here is for some W prime, and then you just copy this because for some W prime such that W R W prime, phi is true there. Diamond. Ah, thank you. Well, thanks. Whereas here, EW, we have this is true if and only if the intersection of the set of accessible worlds and this is not empty. Okay, again, these are equivalent statements. And you can go back and forth here, but it's perhaps, I realize it's doing two things at once is harder than doing one thing, but yeah. Okay, now let's look at an exercise in this gamut copy, if you all have that. It starts with a section on the front that says the origins of intentional logic, and then there are some chapters. And on page 27 of that thing, there's an exercise 2, and we can just briefly go through some of these a little bit, these items there, to get a feel for how this works, right? And can I erase this? Are you still? Some look like they're still writing. Okay. So there is a model there in A, which looks like this. You have two worlds, W1 and W2, and there are arrows going back and forth. I'll put the heads exactly the way it's in the book. And there is one going this way, and that's all, right? And P is true at one of them and false at the other. That's what it means when they write. Perhaps I should use. Oh, I lose the same color. Should be clear. So P is true here, and not P is true here. Okay. And then we are asked, what is the truth value of these sentences down there at these various worlds? And let's just do one or so of these. So for instance, at W1, what is the truth value at W1 of the sentence? If P is necessary, then P is necessarily necessary, right? That's number one. If box P, I now omit the subscript here. So all these subscripts, they are not so important. Then box P, right? Is this true or false at W1? And, well, you can do this in a very systematic and sort of mechanical way. This is true if and only if what? Okay. If and only if this is false or this is true, right? I did that because the arrow is the main connective in the sentence, and the way the arrow is defined is just this, right? This is false or this is true, which is the case if and, well, now actually we have to sort of branch out and look at this separately from this and see. Perhaps it's already false at W1 and we are lucky. We don't have to look at the other side. And of course it is, as you can see, but if you do it in the official way, following the definitions, then you have to take this step, so if and, wait a minute, I don't need to copy this again. So this is false if and only if, well, what is false? So let me write it, we have, yeah. For some W prime such that W1 R W prime, this is false. Because remember, we had a clause for when this is true, right? It's true if and only if P is true at all accessible worlds. Well, here we need to know when it's false. Well, it's false if there's a counterexample to the truth of the sentence, right? If there is a world at which it is accessible and where it's false. And so, okay, we see it's false at W2, W2 is accessible, so we're done. This whole thing, the whole sentence up here is true at W1. That's all, right? We would not be done so quickly if we did it for W2, because in that case, as you can see, there is a world, there is no world that is accessible where P is false. Should I go through that as well? Are you done copying this? Can I just replace this with W2, 2, 2, because we are still looking at the same sentence, right? Now, is this the case at W2 as well? So the whole thing was true W1. Now, do we have this? No, we don't, because the only world accessible is W1, and there P is true. So this whole statement here is false, the first part of the disjunction, okay? Because necessarily P is actually true at W2. So we have to look whether, so the whole thing is false, we have to look whether this is at least true. Well, is it the case that, okay, so for all W prime such that, ST always means such that, right? W2 R W prime, this is true at W prime. Which in turn is the case if and only if for all W prime such that W2 R W prime and I'll just write another for all here, right? For all W double prime such that W prime R W double prime, this is 1. So are all all the possible paths that involve two steps, do they all end up in a P world? That's the question, right? Is there no way to take two steps and finish up in a non-P world? If that is the case, then our sentence is true. So, well, we have this two-step thing that goes to W1, and there P is true. We also have this two-step path which takes us to W2, and there P is false. So this part of the disjunction is false as well, just like the first one. And so the whole sentence is false at W2. Okay? So if we take this and give it a name, just let's call it phi, right? And we can say that phi is true at W1 and false at W2 in this model. That's what we determined in this way. Okay. So far, so good. And then with the other things, you can do the same thing. It gets a bit tedious, right? It's cumbersome, but not really hard to do this, right? So that's how truth values of these modal sentences are determined at individual worlds in the model. Now there are, however, three kinds of statements you can do, you can make about sentences. Two of them we can already talk about here. So we know that phi is true at W1 and false at W2. Those are statements about the truth, right, of the sentence, which is always relative to a given particular model as a possible world, right? Truth at some W, given M, say, in the model, especially given V, the valuation function, that is important. Right? Without that, you wouldn't know whether it's true or not. But there is also validity in a model. These things are on your handout, by the way, of yesterday. I'm still on the first page of section 6, so we haven't proceeded very far, but here in the middle we say truth, validity in a model, and validity on a frame. We haven't yet talked about the frame. Validity in a model, that is easy. It's truth in all possible worlds in the model, right? Well, truth at all W in the set of worlds. And so we know that that sentence phi that we looked at is not valid in the model. Okay? Even though it's true at W1. There is a world where it's false, so it's not valid in the model. And there's a third kind of statement we can make about sentences, which we get when we consider what's called the frame of the model. So a frame F is a set of worlds, non-empty, with the accessibility relation and without the valuation function. So this is just the accessibility relation in itself. And now we can ask, is the sentence valid on the frame? Which means, so let's see, oh, where's my yellow? Validity on the frame. Validity on a frame, which is validity in all models on that. You can build on that frame. Okay. Validity So let me write here in a frame WR, and then we have here validity in all models WRV, where this WR is the same as the frame, and then V is some free variables of all possible valuation functions. Okay, is the sentence valid or not? In this case here, the frame of the model is this structure without the truth assignment, and in fact also then without this, of course, because this depended on what we were given. So that's the frame of this model, just the accessibility relation. And if we ask now, is a sentence valid on this frame, then we have to consider all possible ways of assigning truth values to sentences. P, P not P, not P, P, not P, not P. These two worlds, right? And then for every other sentence as well. So there are lots and lots of valuation functions. If you have many worlds, it quickly gets out of hand. You cannot really check them by enumerating all of these V's, right? But it's the idea. Validity is that. Now we saw that our sentence, which looked like this, if P is necessary, then P is necessarily necessary, was already not valid in this model that we were given, so it's not valid on the frame either. Okay, that's we already know that because the V that we were given already made it false at W2. There are valuation functions that make it valid. If we have P on all these things, then this is certainly valid. Right? If P is true at all worlds. And it's valid in the model. However, there is a model where it's not valid, so therefore it's not valid on the frame. Why is this so interesting? Well, because there is a clear and interesting connection between the properties of the accessibility relation and the sentences that are valid on that frame for the accessibility relation. In particular, this is not valid on this frame because this is not transitive. If this were transitive, then this would be valid. And if this were valid, then this would be transitive. And this is not obvious. You didn't see this, and that's pretty clear. It's hard to show, actually, that this sentence is valid if and only if the frame is transitive. And you may also remember that this, oh no, actually, we didn't see that. In the table yesterday with these, remember these properties of frames, about accessibility relations, properties of modal basis, about seriality and introspection and so on. The third column that I didn't talk about had a formula of this kind, this form. And it said that this it corresponds to transitive accessibility relations, or alternatively, positive introspection, right? So you can actually use these to characterize classes of frames. So you can say, for example, if you want to talk about serial accessibility relations, right? And you can just say that by giving a particular sentence that is valid if and only if the relation is serial. Okay. So if we explore this a little bit, what are the formulas that characterize certain interesting classes of frames and so on, which correspond to certain intuitively sensible properties like consistency and so on. Then we enter this area of modal logic. That's what modal logicians do. Well, not all, not not all the time, but I guess. We can, for example, do this. Suppose to consider this sentence. If P is necessary, then P is possible. Okay. We may ask, is this valid on this frame? And, well, perhaps we don't have to go through it, or should we? Well, perhaps we should. If we have P here and P here, that's one particular model, right? Then, well, clearly, whatever the truth value of this is, this will be true, right? Because from every world there is an accessible P world, right? So the second part of this sentence is always true in this model. See that? From every world there is an accessible P world. So whether this is true or false doesn't matter. This sentence is valid on this model, in this model, right? Remember also that this is equivalent to saying not necessarily P or possibly P. All right. If we have not P, P is false at all worlds, then in all worlds the first of these becomes true, right? Because there is an accessible world from W1 where P is false, and also for W2. So for these two models, the sentence is valid. And if we look at the remaining two, it's fairly easy to see that there too we have we get that the sentence is valid. So in this case, at W1, necessarily P is not true, right? Because we have this loop here, there is a world accessible at which P is false. That means the first part of this disjunction is true, so the whole sentence is true. Okay, W2, we have, well, immediately you see there is an accessible not P world, so the same thing, right? And you can convince yourself that the sentence is also valid for this model. So the sentence is valid on the frame. So let me just put this. So it's valid, we can check this off. Whereas the other one, the transitivity axiom, the one that goes with transitivity was not valid. Okay, so we still have to ask what actually is, what about this structure is responsible for the fact that this sentence is valid? And it is, as it says in the tables, I mean you already know that because it's in your handout, it's the fact that this relation is serial. If there were no arrow here, then the relation would not be serial, and then we should be able to find a model in which this sentence is not valid. That is, we should be able to assign truth values to these to P, both of these worlds in such a way that the sentence finds a counterexample somewhere. And of course we can do that. I don't know here, the important thing is we should put not P here. Perhaps P. Oh wait, no, sorry. Sorry. No, we should sorry, I apologize. We should put not P here. Then, yeah. So and here it doesn't matter. We could, just say P is here. And now we ask, what's the truth value of this sentence at W2? So what is it? Well, if P is true at all accessible worlds, then P is true at some accessible world. Now remember, vacuous quantification. From this world, we have no accessible world. Therefore, P is true at all accessible worlds. Right? Let me write this out. So it's one if and only if for all W prime such that W. Oh God, I'm sorry. I'm jumping ahead. It's one if and only if this is false, or this is true, right? As before. Okay. And due to this vacuous quantification, we know that this is true, right? Therefore, this has to be true as well. But this is existential quantification, so it is false at W2. That means the whole sentence is false at W2, this whole sentence. And we have found a model in which there is a counterexample, and so it's not valid on the frame. All right. Okay, so this, all of this is a bit tedious.
今の場合だと W1 で P でも not P でもどっちでもいいですか？
W1 で、はい。ですよね。別にそれは今あまり気にしなかったけど、はい、どっちでもいいですよ。W1 で P にすれば、これが真になる。not P にしてもこれが真になる。わかりますか？P だとこれ真。not P だとこれ偽真。両方真になる。だからそれは別に関係なく、つまりこれが真じゃない可能性が一つぐらいあれば、ね、それでもう十分。はい。Any other questions? We can also prove this more generally, because so far we only have talked about this particular model. This is a fairly simple axiom. If necessarily P, then possibly P. We can say that this is valid on F if and only if F is serial. Now this is something we might want to prove, right? And we can. So let's see. Are we in time? We have this if and only if, okay? So this is a conditional that goes in both directions. That means when this sentence is valid, the frame has to be serial. So we have this arrow, and when the frame is serial, this has to be valid. So we have the other arrow as well, and we can look at them both in turn. And F is serial. Remember what that meant? What that meant for all W, there is a W prime that is accessible. Okay, that's all. Now, if we look in this direction, the claim is that if the sentence is valid, then we have this property. And we can prove this in various ways. One way of doing this is just to assume that we have, so let's see, suppose that we actually have a frame on which this is valid on f for some f, and f is not serial. Now this should be impossible, right? If this conditional in this direction holds, then this should be impossible. So we should be able to derive a contradiction. Well, f is not serial. That means there is a world, right, that has no arrow coming out of it, such that there is no W prime, WR, W prime. So somewhere in this model, it can have lots of worlds, whatever. There are arrows going around, I don't know, something like this. But so suppose there is a world, maybe it has an arrow coming in, but none going out. So arrow comes in, or whatever, none comes out. And there has to be such a world. So let W be that world, okay? And then ask whether this can possibly be true at W, whether there is a way of assigning truth values to sentences in such a way that this becomes true at W. And there can't be such a truth assignment. This sentence is necessarily false at a world like this. Why? Because, well, first of all, since nothing is accessible, you probably believe me that it doesn't depend on any other worlds. Right? So suppose P is true at this world, then, well, the first part, necessarily P, is true, right? Because there is no accessible world. Again, it's vacuous quantification over all accessible worlds. This is true, but this is false, because, again, there is no accessible world. There is no, in particular, no arrow going around or anything like that. If we have not P, it's the same thing. It doesn't really depend on what the value of P is at this world. The sentence cannot be true there, because this is always true, and this is always false. So I'm abbreviating this proof. I'm not writing all these steps. But if you look in the other direction, we can do the same thing. Now we have to say, suppose f is serial, and the sentence is not valid. Is not valid on f. Now, well, then this means that there is, for some, so it means for some truth assignment V, right, there is a world such that V W of the sentence is false. Right, that's what it means for it to be invalid. And again, if our claim holds, then this should be impossible. It should be impossible that both of these things, this and this, are true. Well, let's see here. So there are all these things. There is a V and there is a W. Okay, let's see. What do we know about W? Well, we know that this sentence is false. That means V W of this is true, and V W of this is false. because that's the only way in which a conditional of this form can be false. Okay. Now, suppose here, let this be our V. There are various structures that we can think of. So, you know, we can have arrows coming in, going out, there are other worlds around, it may have a loop around itself, whatever. What's important is we know that the frame is serial. There is an outgoing arrow. That's by assumption, we assume that. So it either goes around or it goes somewhere else. There's at least one arrow going out. That means that the truth of this is not due to vacuous quantification. There are, in fact, it's really true, there have to be accessible worlds, and P is true at all of them. But then this cannot possibly be false. So again, we have derived a contradiction, and we have proved in this somewhat informal way, that this is in fact true. That this is a sentence which characterizes all and only, class of all and only the serial frames. So, and for other important properties, we have these other sentences that you already have in your table, and we don't need to go through all these proofs one by one. There's no time for that. The other ones, the one for transitivity is a bit longer, but it's the same kind of thing. You can prove them in this way by deriving contradictions. Can I take this off? Yes. So we have this corresponding to serial frames, serial, and we have other ones, right? If necessarily P, then P. That, just look it up. It's better than all reflexive relations. And this we've already seen, transitive. This was, we've not seen this, but it's another one, Euclidean. Okay, let's stick with these. I don't know if we need another one. You sometimes then see names of systems. If you read this literature in Modal Logic, you see things like my model, or whatever, my accessibility relation is a model of some kind, like S4 or S5 or KD 4-5, things like that. Have you ever seen this? I'm not sure. It happens. And this is, well, there's an old tradition, and all these things they have, there's some reason why they are called this. But they all correspond to certain collections of axioms of this kind. What is an axiom? Well, it's something you assume to be true. Something, you know, like I said it yesterday, if you decide that you are now talking about consistent modal basis, and you can just say, okay, in all the modal bases I consider this is valid. Okay. And then since you can assume this, you can prove further things based on this assumption, right? That's what axioms are for, to prove other, you know, derive other sentences. And now these sentences have names when they are used as axioms. And I should also say here, well, I'll say it in a minute. I don't want to get them wrong. So this is, it's all in your handout. This is called T. I think that T comes from truth. I'm not sure. I don't know. The other one, serial. What was That was called D, which is because it's often assumed for deontic logic, although there's no principled reason for calling it that. It's just for historical reasons. This is called 4. Sorry to say. And this is sometimes called 5 and sometimes E. Let's say 5. E for Euclidean. This comes from particular papers that people have written where they numbered their examples in a certain way, and then these things took on a life of their own, and then they just have these names. Now, to get a real system of modal logic, you need to add these sentences to a certain basic stock of 5 things. There is a sentence, another axiom, K, which has this form. If this is true, then so is this. Now, I should say this K, it's a bit uninteresting, but it is, well, because I guess it is true on all possible models of this kind. You cannot construct a frame on which this thing is invalid. As long as you're talking about possible worlds and the usual assumption that you make, like law of excluded middle and so on, this has to be true. It's actually intuitively pretty clear why this must be the case, right? If the first part means there is no world in which P is true and Q is false, right? Because this conditional is true at all worlds, right? There's no world at which P is true and Q is false. At all of them, the thing is true. Well, there are various ways in which there can be no world at which P is true and Q is false. One of them is that P is true P is true at all worlds. So we have P, Q, 1, 1, 1, 0, 0, 1, 0, 0. And then we have, if P then Q, there's 1, 0, 1, 1. What the axiom says is that there is no world of this kind, right? All the worlds are like these. One of these 3 sets of circumstances are true at all possible worlds. Okay. Now then, in particular, if all worlds make P true, that means that they all make Q true. It's that simple, and this cannot possibly be otherwise. It just follows from the definition of these logical connectives. Okay, this is K, named after Kripke, Saul Kripke, the inventor of these models and frames. And there are certain rules of inference. I don't want to go through them. It's in your handout. You have certain ways of deriving more sentences from a set of given sentences like these. You can then substitute items in here. For example, this is one particular atomic variable, but if you have the full system, you know that the same structurally the same sentence is true, valid on all serial frames, regardless of what you have there. So, for example, something like this, necessarily P, if P, then Q, therefore possibly if P, then Q. This is also valid on all serial frames, and so on. So you can substitute things. You can apply more disponents and so on. So there are, in addition to K, a few more things. And even more obviously, let me call this PL, or what do you have on the handout? PL or PC? PC, the third axiom that says, if alpha is a tautology of propositional logic not involving any modal operators, then alpha is an axiom. This one too, both of these are always valid on all frames. Okay, so they are kind of not so interesting in characterizing certain classes, non-trivial, interesting classes of frames. These just are there for logical reasons. But now if you have, for instance, K and this PC, let's see. K plus PC plus these rules of substitution and so on that I added. So I put 3 dots here for things like more disponents and so on. Then you have a system called K, which I will write with yellow chalk. This is a set of these axioms, right? And you're guaranteed that the sentences or the axioms there are characterized as a set of all frames, because it contains these 2 things which are valid on all frames, and then certain rules that are also safe to assume are true. But then more interesting, if you add to K certain other things, then you get other modal systems. If you add T to K, you get a system which is called T, and corresponds to all serial frames. All right. If you add D to K, you get a system, a set of axioms called D. I don't know why. Oh yeah, D. That characterizes the set of all reflexive. Oh, did I mess this up? This is sorry, should have said that. Reflexive serial, like this. I switched them, right? That's easy. Thanks. Easy to put on the board. But perhaps most interestingly, if you add to K these axioms D, 4, and 5, you get what I call K